Hi, in this video we are going to learn about Muskingum routing, and this is mostly used for routing flow through channels, so we will also call this as Muskingum Channel Routing, or in most books it is just called Muskingum Routing. Okay, so what we are going to do is, since we are routing flow through a channel, I will draw a channel here, and then we have a flood wave traveling through the channel. So in the linear reservoir we saw a horizontal water surface, so in this case we are seeing a inclined water surface. So this is our input input hydrograph, and then what we have here is Q, and then we can divide this storage into two parts, and this is called the prism storage, which is a rectangle, and what we have here is a wedge storage, which is the triangle. So the total storage that we have is, so S is our storage, and that can be divided into S prism plus S wedge. Okay, now since we have input and output, what we can also say is this portion is same as our output, and this wedge portion is our I minus Q. Okay, and if that is the case, then we can write an expression for the prism storage and the wedge storage. So prism storage, we have a rectangle here, and we can think of that as a linear reservoir. So I'm going to say that is going to be K times Q, and we have already used this in the linear reservoir problem. And for the wedge storage, what we have is I minus Q, so that part becomes K times X times I minus Q. So instead of just KQ, we have now K times X, and this is our I minus Q. So we have added one more variable here, so that X is basically, it's a weight of inflow versus outflow. Okay, and since this is a weight of inflow versus outflow, if X is equal to 0, S wedge will go away, and we end up with linear reservoir problem. Okay, so we can think of linear reservoir as a special case of Muskingum routing where X is equal to 0. Okay, now you may ask what value of X should we use. So X is usually between 0 and 0.5, and as I said, when it is 0, it it is a linear reservoir problem, and the max you can get is 0.5, but most typically X has a value between 0.1 to 0.3. Okay, and we will see this when we try to derive a value for X by using observed data. So how do we find K and X? We will see in the later video, and for that we need observed data. So for now, this is the expression we have for the total storage, and so this is our first expression. And if you remember, for routing flow through a reservoir, or in this case channel, we need two expressions. One is the storage and inflow outflow relationship, and the second one will be the continuity equation. and in the linear reservoir routing problem we use this discrete form. So Sj minus Sj minus 1 divided by delta T is equal to Ij plus Ij minus 1 divided by 2 minus Qj plus Qj minus 1 divided by 2. Now again, similar to the linear reservoir problem, our I's are known. The inflow hydrograph is always known, and delta T, K and X also given or known, and if K and X is not known, they can be derived. So this can be derived using data of I and Q, and we will see how to do that later. Okay, and then initial condition Q0 is also known or assumed. Okay, so this is our second expression, and then this is our first expression, and we do the same thing that we did for linear reservoir. So I will rewrite the storage minus Sj minus 1 over delta T is equal to Ij plus Ij minus 1 over 2 minus Qj plus Qj minus 1 over 2. Okay, so this is what we have, and similar to what we did for linear reservoir, now we will replace Sj with the storage expression that we have for prism and wedge storage, which is this. Okay, so I'm going to go down. So for Sj, I'm going to write K times, or let's simplify our storage expression. So we have Kq times Kx I minus Q. Okay, so S is equal to Kq plus Kx I minus Q, and we can simplify. I can bring K out, then I have Xi plus 1 minus Xq. Okay, and then we are going to replace Sj and Sj minus 1 with this expression. So if I do that, what I have is K times Xij plus 1 minus Xqj minus K Xij minus 1 plus 1 minus Xqj minus 1 is equal to I, and then I need delta T over here, so this is going to be K over delta T, K over delta T is equal to, then I have Ij plus Ij minus 1 divided by 2 minus Qj plus Qj minus 1 divided by 2. So we are going to simplify this expression and then end up with an expression for Qj, which will be the discharge value for the current time step. So to do that, what I'm going to do is I'm going to keep Qj on the left hand side. So what I have is, and I will also bring 2 on the other side. So if I do that, I have 2k over delta t. Then I have 1 minus x qj on this side, and then I have qj on this side also. So this is minus here, which means this will become plus on this side. Okay, and then on this side we'll start with ij. So again for ij I have kx over delta t times 2. So 2k x over delta t, and this will become negative on this side. So this is positive here. So on the right hand side that will become negative. So this is minus 2k x over delta t times ij, and then I have ij here. So this will be ij. Okay. And then we will write an expression for ij minus 1. So ij minus 1 is negative on the left hand side, so this will become positive. So this will be kx over delta t times ij minus 1, and this is positive ij minus 1, so this will stay positive ij minus 1. And then we have qj minus 1. So qj minus 1 is negative on this side, so that will be positive k 1 minus x over delta t qj minus 1, and then we have negative qj minus 1 on the right hand side, so we have qj minus 1. So if we simplify this, so what I have is qj and then I say 2k 1 minus x plus delta t over delta t. Okay, so you can see we have delta t on only for this part. So what I have done is I have multiplied this qj by delta t, and the whole denominator is delta t now. Okay, so similarly for ij, I can multiply ij with this delta t, so that will be delta t minus 2kx over delta t, and for ij minus 1 we have delta t plus 2kx over delta t. Okay, and then for qj minus 1 we have 2, we have k. So I think I forgot to add 2 here, so this should be 2. Okay, because it was, we brought this 2 on this side, so that's why we have 2k over delta t, and that's why this should also be 2k over delta t. So what I have now is 2k 1 minus x minus delta t over delta t. Okay, and then this delta t will get cancelled from all the expressions. So what I have now is qj, and I'm going to bring this coefficient for qj, which is 2k 1 minus x plus delta t, as denominator on the other side. So I have delta t minus 2kx divided by 2k1 minus x plus delta t. That's my ij. Similarly, I have delta t plus 2kx divided by 2k1 minus x plus delta t, ij minus 1, and then I have qj minus 1, which will be 2k1 minus x minus delta t divided by 2k1 minus x plus delta t, and that will be qj minus 1. Okay, so now similar to what we did for linear reservoir, I can replace those expressions with C1, C2 and C3. So Qj is equal to C1 times Ij plus C2 times Ij minus 1 plus C3 times Qj minus 1. So again, if I'm solving this for Q1 times I1 plus C2 times I0 plus C3 times Q0. So this is known, and this is our initial condition which is known. So we solve for Q1, we get Q1, and then we solve for Q2, which will be C1 times I2 plus C2 times I1 plus C3 times Q1, and so on. So this will be similar to what we did for linear reservoir, and similar to the coefficients 2c1 plus c2 is equal to 1. So in this case, if we add c1, c2, c3, we end up c2 plus c3 is equal to 1. Okay, so this condition satisfies in Muskingum routing, and similar to the stability criteria we had for linear reservoir, which was for linear reservoir we had delta t over k should be less than or equal to 2. Similar to that, we have condition for Muskingum, which is 1 over 2 1 minus x should be less than k over delta t, which should be less than 1 over 2x. So this is the stability criteria for Muskingum routing. To avoid negative values of Q. Okay, so this is the expression we have for solving or for finding a discharge hydrograph if we know the input hydrograph through a channel. And to do this, we need inflow hydrograph, which is all our eyes. From delta t, k and x, we can find c1, c2, c3. Make sure we satisfy this criteria and this criteria, and then we should be good to go. Now, how to apply this expression, we will see that in the next video when we do a numerical example. Okay, and again, if you put x equal to 0 in this expression, you will end up with this part. Okay, so as I said before, linear reservoir is a special case of Muskingum channel routing where the wedge storage is equal to 0, which we can do by equating x is equal to 0. Okay, so this is it for this video, and in the next video we will do a numerical example for Muskingum routing. So I'll see you next time. Thank you.